This is the last sections of these chapters, and that's about the design of the shaft, and also talk about the concentration of the stress. And so this page basically talk about the design of the transmission of shaft, and to use shafts to transmit torque, and basically that is provided the given information will be parameter will be including the power, for example the power from the engine, and then the speed is the rotation speed of the shaft. Okay, so usually we have this formula: P is the power, and omega is the rotation angular RPM. Sorry, omega is the angular rotation of the shaft. And if we convert it into F, basically F is the RPM here. So, okay, so basically that is the number, the frequency, basically the frequency is in hertz. Okay, so basically in hertz, that means, for example, 6 hertz, that means the you have the 60 times of rotation in second. Okay, so basically that is the information here, and P is a given power. So, and T is the torque we've been studying in our shaft. For example, here this is our model. So if this is the torque here, and then here material properties, geometry and dimension here, then we can calculate the tau equal to TR over J, and the phi angle of the twist equal to T L over GJ. Okay, so basically the T is related to the formula we've been applying here. So we keep this in mind, then we can see how much we can do. The second topic in this section is talk about the stress concentration. The stress concentration happened at where the geometry become non-uniform. So for example, here we have the bigger shaft, and here we come to the smaller one. So around here that has the geometry discontinuity, so that is where the this concentrated stress happens. And either here we use fillet, and this called the fillet radius, even we use the fillet, and that can help reduce the stress concentration, but cannot eliminate. Okay, it will help reduce, but wouldn't be able to eliminate the stress concentration. So here, keep it in mind, at any location that's a stress concentration, and here the stress concentration basically is deviated from what we've been formulated. So again, for this equation that is pertaining to our shaft model, that is uniform shaft. Okay, so this shaft has a radius C, and then from this case we know the formula. For example, this shaft is circular. Okay, so let me enlarge here. So that's a circular shaft, and say if this is under torsion, so this is the center here. So we know the distribution of the stress at R and equal to tau as a function of R equal to TR over J. And the maximum occurred at the outer surface when R equal to the radius C here. Okay, and so that is the formula we use. However, right now, because for our shaft has become non-uniform like this one, so basically around here, like I mentioned here, so basically the larger stress and concentrated stress will happen. So to correct, to come up with corrections of using based upon this formula to predict the concentrated stress, and here we again, similar to our previous section, we multiply with a factor K. Is called the stress concentration factor. Okay, the concentration factors, and multiply this concentration factor with the quantity we learned here and the maximum for our case, the maximum for our simple model, the homogeneous uniform model is TC over J here. Okay, so pre-multiply what we have learned with stress concentration factor, that will allow us to very good, pretty well estimate this concentrated stress, the maximum stress happening in this kind of practical non-homogeneous non-uniform shaft here. Okay, so let me explain in this equation. This equation involves two quantities. One is to determine the K value. The K value and basically is based upon the geometry of this kind of shaft, and we are given the diameter of the larger side and diameter of the lower side. So you can first one determine the ratio, and here you can determine which curve you have to use. And then also depends on the ratio between the fillet radius to D, and you determine this one. So with the two quantities, you should be able to uniquely identify the value of K. So that we solve for how to determine the K value. The second quantity is to determine this one. This quantity must be calculated, keep this in mind, must be calculated on the smaller shaft. Okay, so you calculate this quantity based upon, for this example, say the smaller shaft is D, so for this case the C should be equal to D divided by 2. Okay, keep this in mind. This is, if you apply this calculation to say a larger shaft, then you will get a mistake in your solution. So we take a look at this example here. So we use this non-uniform shaft for load transmission here. And again, the load transmission is P equal to 2 pi T F. And here the F is the about the rotation speed of rotation, and here the F is in Hz, okay, in the hertz, okay, and P is in power. For example, if we are in Newton meters, then the power should be corresponding in the okay, we'll look at that one, watts. Okay, so in watts. So so we'll look at this problem here. So we know the frequency, for this case, the frequency F equal to 50 hertz. Okay, we are given here. So we are given the fillet dimension, are equal to 8 inch, and then here the maximum allowable stress 45. So under this case, you can see the maximum stress, again, under our design criteria, it should be smaller than the allowable. So that is 45 MPa. Okay, so what is maximum? Maximum is K times Tc over J. Again, that is the previous this equation here. Okay, and so K, what is K? Let's determine K. The K value from here, we know we can determine D. We need this quantity, for this quantity equal to 2 here. Okay, so we simply pick this, and then R over D here is 0.26, about 2.7. So here we can look at here, that is about here. So along this curve and 2.7. So let me follow up this one. So go to here, about here. Okay. So that is where K value is. We estimate is about 1.18. If you say, hey, can I estimate 1.2? I think that's okay. So once we have determined K value, then here is this. And then again, this quantity must be calculated based upon the smaller shaft. So from here, the C should be equal to 15 millimeter, and J equal to pi over 2C to the fourth power. So put everything together and subject to these criteria. Then from here you should be able to determine the T is less than or equal to 202.17 Newton meter. Okay, so right now the T has determined T is less than that one. So basically you can determine therefore P equal to 2 pi TF, and then that should be equal to less than or equal to 2 pi 202.17, and multiply with F 50 Hertz. Okay, and again utilize all the unit here. So that one P must be less than or equal to, put it this one is 63500. Okay, so that is watts, and all the calculation, if you put the meter, newtons, hertz together, that should be watts, and that equivalent to this one here. Okay, and that basically equal to 60.3 kilowatts. And we take a look at another example here, and the same shaft, and here right now again the P equal to 2 pi TF here. And right now for this case, P equal to 45 kilowatts, 45,000 watts, okay? And then equal to 2 pi times, and here we want to know what is the maximum speed can be allowed. Okay, so we want to determine what is F here, and then we need to determine T. Okay, so what is T? Again, we follow up this the maximum stress, and the allowable shear stress is 40, so less than the allowable, so that is 40 MPa. Again, the maximum equal to K times TC over J, and by repeating the previous example there, the C is the information about the smaller shaft and 15 millimeter, J pi over 2 C to the fourth power. And what is K here? And for K here, and say here we want to determine D capital D over D, so that is 2 here, so we pick this curve, and then R over D is equal to, for this case, is 0.2. So R over D 0.2 pointing to here, so that is this point for K, and that is about 1.26. Okay, so basically from here 1.26, we put everything together, so from solving this equation, then we can determine T is less than or equal to 168 kilonewtons per meter. Okay, so we plug in here. So basically the T equal to say right now the maximum is 168 times 10 to the 3 and Newton meter, okay, and times F. So by solving this one, then F should be calculated 42.6 and hertz, and this is the maximum speed and for this shaft here. Okay, so that is for these sections, and then also this marked the end of these chapters.